Hi everyone, it's 3 p.m. So welcome to our probability and analysis webinar. Our speaker today is Piotr Nayar from the University of Warsaw, who's going to tell us about entropy for Gaussian quadratic forms. And let me also remind that the talk is being recorded, but only Piotr's video is being captured. Piotr, please, the floor is yours.
Okay, thank you, Thomas. And of course, thanks go to organizers for giving me this very nice opportunity to give the talk here. So maybe first some statistics. So we will have 14 slides. 3 of them will be non-mathematical, including one picture. There will be almost no jokes. And let me also tell you that this is a joint work with Szymon Zwara, who is a student at the University of Warsaw. Yeah, okay, this doesn't work. Okay, it works. So this is Szymon. And of course, the question is, why is this picture so boring? And the answer is that I have much better pictures, but all of them are too funny to be included in such presentations. So this is what it is. And so here's the topic of the main object of study in this talk. Now it is the entropy. So entropy of a one-dimensional random variable. So X is a random variable, and we assume that it has a density F, and then the entropy of X is given by this formula. So sometimes I will write H of X, sometimes it's going to be H of F, where F is the density of X, and this is simply minus integral F log F. And you can also write it like this. This is the expectation of minus log F of X, because here we integrate against F, right? So there are some well-known features of this functional. So for example, it is invariant under scaling, under shifting, and also if you scale X by lambda, then this term log absolute value of lambda pops out. And then we will also be using the variance of X, which is given by the familiar expression. So let me give you the motivating fact, which is super standard, and it says that whenever you have a variance-1 random variable, then the entropy of X is upper bounded by the entropy of a Gaussian. So the Gaussian random variable standard N01 maximizes the entropy among all random variables with variance 1. Okay. So we should have this in mind. And then I will just give you the proof of this, just to make sure that we have all the tools that I will need later. So this is the first and the most basic tool. It's a variation of principle for the entropy. So if you have Fg, two probability densities, then the entropy, which is minus integral F log F, is upper bounded by minus integral F log G for any density G. So you can pick whatever you want. And the proof of this is super easy. So there's this inequality that log X, you can do it in many different ways. You can use Jensen's inequality or whatever, but I like to do it in this way. So there is this inequality that log X is upper bounded by X minus 1. And then if you move this integral F log G to the left-hand side, you put these things under one integral, and then you use this inequality, you get this bound over here, and then you can see that this thing is simply 0 because the integral of F is equal to the integral of G, and it is 1. So this is how you can prove this. And then if you want to prove the fact that Gaussian maximizes the variance, the entropy among all variance-1 random variables. You just use this fact in the following way. So phi of x, this is the density of the one-dimensional symmetric Gaussian random variable, n01. And in order to proceed with the proof, we can always assume that the mean of x is equal to 0, because we can always translate x, because this doesn't affect the variance and it doesn't affect the entropy. So if we assume that the expectation of x is 0, then from the variance-1 condition we have the expectation of x squared is 1, which means that the integral of x squared against f is 1, but this is also equal to the integral of phi against x squared. And then the entropy is minus integral f log f. Then we use the variational principle here in the first inequality. Now we write what log phi is explicitly. But now since we have these conditions over here, we can replace f with phi here, because here, the constant here and here the constant is the same, and the integral of f is equal to the integral of phi and it's 1. And then also the integrals of x squared against f and phi are the same. So we have this equality. And then this is simply the integral, the entropy of G. So this is how this basic fact is proved. And then we can ask ourselves the following question. So let's say, because this was very general, so this fact was true for any random variable, any variance-1 random variable. So now assume I have some family of densities f of variance-1, and then you want to ask yourself, okay, what is the soup of the entropy? Only restricted to that specific family. So today we are going to address this question in the following setting. So we'll just take the f to be the family of quadratic functions in n IID n01 random variables. So A is an n by n symmetric matrix. And this XA is just the quadratic form generated by A in n independent random variables, G1 up to Gn. So this is my family, and the question is, what is the soup of the variance? What is the soup of the entropy in this class? And now I should probably tell you what is the condition for XA to have variance 1. So it's pretty straightforward to compute the expectation and the variance of XA, and this is given by these formulas. So variance of XA is just proportional to the sum of the squares of these the coefficients of this form. Okay. And now the theorem that I want to prove today, hopefully, is the following. So if you have a positive semi-definite matrix A, such that the sum of the squares of entries of this matrix is equal to 1, which corresponds to variance being 1/2, then the entropy of XA is upper bounded by the entropy of diagonal quadratic form. So the corresponding to A being proportional to identity. And of course here the coefficients sum up to 1. So this is just the maximizer in this problem. Okay. So this is what we want to prove, and I'll give you an open question. So one open question here is, what happens if I consider general A, not positive definite? So I just take general A, and Well, I have no idea what's the answer. I mean, I have some guesses, but I don't know how to solve this problem. So this works only for positive semi-definite matrices, and I think it will be clear in 10, 15 minutes why is this the case. Okay, so this is what we want to do. So now let me give you the first step in the proof, which reduces the problem to something which looks much easier, I would say. And this is I would say it's an obvious step. So whenever you have a unitary matrix, like rotation, right? Then UG has the same distribution as G, because G is a standard Gaussian vector in Rn, so it's rotation invariant. So whenever I rotate G, it has the same distribution. So when we apply this fact here to my form AGG, I get this, and now I can put U to the I can move it here, and then I got U transpose AU, and then I can use the fact that there is U such that this matrix is diagonal. So I pick this U, and then I can see that I reduce the problem to the diagonal form. So in fact, what we want to do, we want to prove this inequality. So whenever D1 up to Dn are some non-negative real numbers summing up to 1, then this inequality holds. Okay? So this is what we really want to prove. So the equality is for equal coefficients. Okay. And then, so this is a particular instance of a more general problem. So the problem goes as follows. So let's say you have some IAD sequence of random variables x1 up to xn. And the question is, when do we have such an inequality? Holding for all sequences d1 up to dn, let's say non-negative, summing with squares summing up to 1. And it's maybe it's surprising, maybe it's not surprising, but this problem is somehow difficult, and for some cases it is solvable. So for some very simple cases it is not solvable. So let me give you some short description what is known about it. So with Ball and with Thomas, we proved some time ago that in general this inequality will not hold, even if n is equal to 2, and even if x1 and x2 are symmetric. So there are examples such that this is not true, or n equal to 2. On the other hand, with Alexandros Eskenazis and with Tomasz, we proved that if xi are Gaussian mixtures, which means that xi have distribution ri times gi, where gi is a Gaussian, and ri is independent, let's say positive random variable, then it is true for some reason. But you can consider very simple random variables such that this problem becomes very hard. So for example, there's one open problem. Let's say xi are IAD uniform on -1, 1. And then this inequality probably holds. But, well, I think we have no idea how to prove it. Maybe we have some approaches, but no, none of them really work. So this is one open problem. Here's another open problem. So you can ask more general questions. So for example, instead of taking uniform on -1, 1, you can consider, let's say, symmetric log concave random variables. And then you can ask the same question. And this is not, the answer is not known even for n equal to 2. And so on the other hand, from our theorem that I will prove today, you can get that it is true for if xi are gamma random variables with parameter k over 2 where k is integer. And this is actually, this observation is actually due to Alexandros Eskenazis, who mentioned to us that, you know, when you take the squares of the Gaussians, you get the Gaussian gamma distribution. So basically what you can get this result by applying our theorem not with n but k times n, and you take, you know, k times the same coefficients here and k times the, you just take these packages and you can deduce this very easily. So for example, if k is equal to 2, you get you get one-sided exponential random variables. And previously we had like separate section for the proof in this case, and then Alex told us, you know, come on guys, this is objects, right? And then Balczak, who is a student of Rafał Latawa, at least according to Rafał, proved that this is actually true for any gamma random variable with parameter a greater or equal 1/2. So this is basically what's known about the problem. And now, so I guess next 6 slides is the proof of the theorem. And it contains some complicated expressions at some point. So we should stay focused, I guess. But the first step is easy. So recall that we want to prove this, where yi is gi squared minus 1. So here instead of writing gi squared here, I wrote yi where I subtracted 1. And this makes no difference because entropy is invariant under shifts. So I can always, you know, shift. So this got shifted by a sum of di's. So I mean, it doesn't matter because the entropy is the same. But now I benefit from that because I can now say that the expectation of yi is 0. So, and we will see that this is crucial in the proof. So this is the first observation that we can do that. So let's say that let's call this thing on the left hand side, this random variable, let's call it un, and let's say it has density pn. And then the thing on the right hand side is the vn with density qn. And then capital phi n is minus log of this density qn. And this is written in blue because I just to remind me that I have to say here that phi n is some very explicit function and it can be computed. And we will use the form of phi, but not right now. Because as you can see, you know, yi's are, you know, basically this is the sum of squares of a Gaussian, which is the high square distribution. So it is known what is the density of high square distribution. You can compute it, and this is, you know, this is explicitly computable. So we have to have this in mind. And then this is the strategy for the proof. This is what we want to do. So the entropy of this variable un, which is h of pn, this is minus integral pn log pn, and then in the next step we want to use the variational principle and replace this pn with qn. So this, well, I guess it is our only hope to, because, you know, if this doesn't work, then the problem becomes really, really difficult and probably not solvable. But fortunately, this will actually work here. And then, you know, this thing is using this phi n. This is the expectation of phi n of un. And then let's imagine that we are able to prove that this is less than or equal to the expectation of phi n of vn. Then this thing just becomes minus integral Qn log Qn, which gives you the entropy of Qn, and we are done with the proof. Okay? So the only missing step, which is the crucial step, is this thing here with question marks. Okay. So these are the question marks. So this is the inequality that we want to prove. Okay. And now, well, so you want to say that among all coefficients summing non-negative coefficients with squares summing up to 1, the worst thing or the best thing is the sequence of equal coefficients. But it is enough to do the following thing. So keeping the sum of squares fixed, so equal to 1, it is just enough to make 2 of the coefficients equal. Because then you can keep repeating this procedure over and over again. And then in the limit, you will get all the coefficients equal. Or in other words, you can think of it like this. So let's say you take the maximizer. There are some difficult, some technical issues, like you have to prove that the maximizer exists, but this is all easy. So let's say that the maximizer exists. So this is some sequence d1 up to dn. And then if the coefficients are not equal, then you take 2 coefficients that are not equal, and you use this inequality to make them equal. And you actually have to prove that if d1 and d2 are not equal, then this inequality is strict, and it is true. I'm neglecting here some technical issues, but this is actually true. And then you will arrive at contradiction that this was not a maximizer. So basically what you want to prove is this inequality. And then use some continuity argument or something like that. Okay. But so actually you can do something even simpler. So instead of writing sum of diyi from I equal to 3 to n, you just can write some real number s here, and and you can hope to prove this inequality. And if you prove this inequality for any fixed s, so this condition, this is just to make sure that these things are well defined, because phi n is not defined everywhere. It's defined only on a half axis, but you can neglect this thing here. So let's say you can prove this inequality over here. Then you just take s equal to sum of the diyi for I bigger equal 3, and then you average with respect to y3 and yn, and you basically get this thing over here. So this is this is another step towards understanding what we really have to do. So this is written again. So we want to prove that the expectation of phi n of u is less than or equal expectation of phi n of v, where this u and v are given by these expressions. This is basically what was written here. Okay. So now what do we know about u and v? So we know some things. So for example, we know that the expectation of u is equal to the expectation of v, and this is equal to s, because we already know that the expectations of y1 and y2 are equal to 0. And then it is also easy to get that the expectations of squares are the same. So this is what we know. And then we also know what phi n is. So this is what I wanted to tell you, is that phi n is some explicit function. So this is how it looks. It's not too bad, I would say. But the problem in this inequality is that the densities of u and v are very complicated. I mean, maybe not super complicated, but they involve some Bessel functions, for example. And you know, if you want to prove inequalities with this type of objects, you better have some idea how to do it, because otherwise it will not be possible, or you will need to do computations for 50 pages or something. So we need some idea to prove this inequality. And so this is the idea. So this is the crucial lemma that will be used here. So there are three assumptions. So first of all, we have this function phi of x, which has this form. So here I didn't have the x squared term, but let's say I can also have the x squared term. And here it is only important that the tau here is positive, non-negative. So let's say I have such a function. And it is really crucial that this function has this form. Somehow we were very lucky that many things here are just go in the right direction. So phi of x is this, and then u and v are some random variables, real random variables, such that the expectation of u is equal to the expectation of v, and the expectation of u squared is equal to the expectation of v squared. So in our case, this holds. And then there is a third thing that is crucial. So we assume that fu and fv, being the densities of u and v, are such that fv minus fu is a function which changes sign exactly 3 times on the set where it is defined. And there's this addition that it is positive before the first sign change. The crucial thing is that fv minus fu changes sign exactly 3 times. And then the conclusion of the lemma is that it's what we want to prove. That the expectation of phi of u is less than or equal to expectation of phi of v. Okay.
Piotr, sorry, I think there's a question about Cn. What is Cn?
Okay, so Cn is some constant. It doesn't depend on x, it's some constant. It's a complicated, I don't know what, I don't remember what this constant is, but this is a constant, okay?
All right, thanks.
And then, okay, so this is the lemma. So I repeat it here. And of course, and also the proof of the lemma is a crucial thing. So this is the proof. So, you know, we want to prove that the expectation of phi of v is bigger or equal expectation of phi of u. So this is written here. But this is equivalent to what is written here. So here the difference is that I subtracted from phi, you know, some quadratic function. And I can do this because the integral of this quadratic function against this difference phi v, fv minus fu is equal to 0, because, you know, the expectation of x of u squared is equal to the expectation of v squared, and the expectation of u is equal to the expectation of v. So these integrals, and also the integral of fv itself is equal to 1, which is equal to the integral of fu. So this integral here is equal to 0, so I can subtract this from phi for any a2, a1, and a0. So I can do that. And then let's say x0, x1, and x2 are sign change points of fv minus fu. So here I assume that there are precisely 3 sign change points of this difference. So then we choose a0, a1, and a2 in such a way that this function, this difference here, which I call psi here, that this difference vanishes at these 3 points. So fv minus fu changes sign in x0, x1, and x2, but I also made this bracket to vanish in this at these points. So I will be done with the proof if I could show that the integrand is positive. I mean, I will have that the integrand is positive because the function psi changes sign exactly in points, I mean, only in points x0, x2, and x0, x1, and x2. So psi is some, well, it's some concrete function, right? It's some quadratic. If I subtract quadratic function here, I still get something quadratic here. And then this log x minus L. So this is some very, very concrete function. And I made it to have, you know, at least 3 sign change points. So it has sign change, I mean, it has zeros at x0, x1, and x2, but then you can easily prove that these are sign change points. So, you know, this function here, it changes sign exactly in the places where this difference changes its sign, which means that the integrand is positive. And by the way, you know, we assume that this difference is positive before the first sign change point, which means that, you know, before the first sign change point, this is positive, but this is also positive because, I mean, due to the, you know, if x goes to L, this goes to plus infinity, this function phi of x. So the sign of the integrand you get from this last assumption that about the difference of fv minus f. Okay, so this is basically the crucial lemma and its proof. The crucial thing is to subtract this quadratic function here and play with it, and make the sign change points of this and this equal. Okay, and now, so what do I have to do to finish the proof? So I have to do only one thing. I have to show that for my v and my u, this third dot is true. So I have to show that fv minus fu, you know, changes sign exactly 3 times and is positive before the first sign change. Okay. So the first step is to show that it must have at least 3 sign change points, this difference. And this is, so for this we will need a lemma. The lemma is super easy. So let's say you have a function g, which changes sign exactly k, at exactly k points. And assume that all of these integrals vanish. So the integral of g and the integral of g, g times x and g times x squared up to g times x to n minus 1, all of these integrals vanish. And then the claim is that k is bigger or equal n. And so this is the proof. So assume that this is not the case, and k is less than or equal n minus 1. And then it has some sign change points, x1 up to xk. So we cook up this integral and this expression, and we observe that the integral of this is equal to 0. And why is that? So this thing here is a polynomial of degree k, and k is less than or equal n minus 1. And all of these integrals here, there's an assumption of the lemma that they are equal to 0. So, you know, I integrate g times some polynomial, and from the assumption, I know that all of these, you know, terms in this polynomial, when integrated against g, will be equal to 0. So this is equal to 0, but on the other hand, these were sign change points of g. And, you know, the sign change points of these factors x minus xi are the same. So in fact, this integrand does not change its sign. So this is basically a contradiction. So it has a fixed sign, so it cannot, the integral cannot be equal to 0. Okay, and then how do we use this to conclude that our difference fv minus fu changes sign at least 3 times? So for this, we don't need the form of fu and fv. We just need the fact that the expectation of u is equal to expectation of v, and the expectation of u squared is equal to expectation of v squared, which we have. And then, which means that, you know, these integrals are equal to 0 for I equals 0, 1, and 2. Well, the case I equals 0 just follows from the fact that these are probability densities, so the integrals are equal to 1. Okay? And then we can just apply the lemma for g equal fv minus fu. So the lemma tells me that whenever I have these integrals equal to 0, then the number of sign change points is at least n, and n is equal to 3 in our case. So this is basically the proof that I must have 3 sign change points in this situation. But then how do I prove that? So the very last step in the proof is to show that I cannot have more sign change points for this function fv minus. And for this, for this statement, it is maybe technical, but it's not that technical. As we will see, the proof will fit in basically one slide. So the next slide is the last slide, I think. The last mathematical slide, at least. And we will show that it cannot have more than 3. The difference of fv and fu cannot have more than 3 sign change. So now I will need the form of u and v. So this is how u looks like, and this is how v looks like. And since I want to deal with the number of sign change points of these densities of these guys, I just neglect s here because it makes no difference. And then for these 2 guys, we will have to compute the density. I will not compute it here, I'll just tell you what it is. It is easily computable. So this is the density of fu. So you have some exponential here. It is supported on some half-line. And it involves some Bessel function, something like this. Okay. So this is the expression, and fv, well, fv is something simpler because you have equal coefficients here in front of y1 and y2. So this is something rather simple. This is just an exponential times this indicator. Okay, and then there is one easy sign change point that is always there, and you can easily understand why. So the first sign change point is this point minus d1 plus d2 here. Because look here, so this function fv, it is supported on half line, and this square root here this is bigger than this thing d1 plus d2. So when I look at the difference fv minus fu, it is first positive because I only have fv. Fu is not, it's still 0 there. And then once I get to the point minus d1 plus d2, fu has discontinuity and it jumps from 0 to some value. And you can easily check that this value is bigger than the corresponding value of fv. So, fv minus fu was fv, and it was positive, but then suddenly at d1 plus d2, it becomes negative. So this is the first sign change point. And then, both of the functions to the right of minus d1 plus d2, both of these functions are active. So I just have to show that when both of them are active, so for x is bigger than minus d1 plus d2, I can have only 2 sign change points. Okay, so then to investigate so this is what I said. And then on this interval minus d1 plus d2, on this half line to infinity, where both of them are active, in order to understand the number of sign change points, which take the logarithms of these functions. So the number of sign change points, is the same, of course. And what can we say about the difference of logarithms? So, so the logarithm of this, so from this factor, you get some affine functions. From this factor, you get, you get log of this I0. And from FV, you get another affine thing. So this is basically log of I0 of some affine function plus something affine. But now, the crucial thing is that I0 is log convex, as we can see, by Helder inequality. So this is, or we can say that it is a Laplace transform of something. So if you just write down the Helder inequality here for this integral, you will see that log of I0 is convex. So this is the super classical thing. So log of I0 is convex, which means that, if I compose this with this affine function, it is still convex. So this log I0 of this thing here, it is convex, plus affine, it is still convex. So this just tells you that your function is convex. So, and the convex function cannot have more than 2 sign change points on the interval where it is defined. So this proves that this function can have only 2. Well, we already know that it has altogether, it has to have 3 sign change points. So it has 2 sign change points on I, but it cannot have more. So, this argument tells you that together with this point minus d1 plus d2, you can have at most 3 sign change points. And this basically finishes the proof, I guess. And yeah, okay. So I think this, it is a good time to finish. And thank you very much for your attention and for listening to what I wanted to say. Thank you.
Thank you, Piotr, for the wonderful presentation. Now I guess it's time for some questions, comments, objections, allegations to Piotr. Please.
Piotr, I will ask one question. Very nice talk. Thank you. So you have this 2 homogeneous Gaussian curves.
Yes.
What about dehomogeneous?
This is a very good question, but here the crucial thing was this rotation invariance, right?
Mm-hmm.
Basically reduces it to the problem for this weighted sum of IID random variables. And then for dehomogeneous, I don't think there are tools to tackle this. But of course it's a wonderful question, and it would be great to have some idea how to start thinking about this problem.
Yes, but is there a belief that it should be the one whose all coefficients are equal, and that's the maximizer? Or there is no any such? Yes.
Well, I don't have such beliefs. I mean,
okay.
Maybe you can have a guess, but what to do to approach this question, I have no idea. But yeah, very good question.
Can I also ask one more question? You have this, very often I see this expression, expectation of some function, the sum random variables times coefficients, some di times xi are random variables. Is there some theorem which tells when this function as a function of di's is sure convex or?
Well, yes. So
Does this approach
here's
apply
the
to
thing.
your problem, or it's no?
Okay, so here's the thing. So there are, so of course, if phi is convex, then this function as a function of d1 up to dn is sure convex. Because this is just it's a symmetric function. It's trivial that that this function is sure convex. But the problem is that in the problem you fix not the sum of the i's, but the sum of squares of the i's. You see what I mean? So
Yes, yes, I got it. Okay.
so, and this is the problem. So yes, and yes. So I don't think that there are easy, general description of when this as a function of squares is true convex. It's just, I mean, so you are just asking for a different somehow question, but here what is interesting is that you want to fix the variance, which means that you have this sum of squares fixed. Yeah. So.
Okay.
I have a question from one of the participants. Yeah, there was a raised hand from somebody.
Yes.
Hi, Piotr. Thank you for a nice talk. My question is concerning the psi function that you had, which was this logarithm of x minus L plus a quadratic. And you're able to show that it has 3 points where it changes sign. But how could you conclude that those are exactly the 3 points? Like there are no more places where it can change sign?
You know what you do here is that let's say you have this function, and then let's say it has more than 3 sign change points. Okay, then you take its so these are the zeros of the function. So by Rolle's theorem, if you compute the derivative, it has to have at least 3 sign change points. I mean, at least 3 zeros. But then if you differentiate the log, you get 1 over something, so you get a quadratic equation. It can only have 2 solutions. Basically, this is how it works. And it's super easy to prove that it cannot have more than 3 zeros. I don't know, does this answer the question? Thomas?
Oh, yes. I think it makes sort of sense, right? Rolle's theorem, I guess, is an intermediate value property, right?
The question, he just said that he lost his audio and he will listen to your answer in the video recording.
I see.
That's probably why we can't hear him.
I see.
Good. Any other questions?
So maybe I can ask just, maybe it's a silly question, but in your proof, you did a discrete change, right? You took 2 coefficients and you sort of replaced them by sort of roughly speaking their average, but not quite, right?
Yes.
Could it be that this all equals thing is the only, say, critical point? So somehow there's an infinitesimal characterization also?
I would say It's a good question, but I don't have any opinions about the critical points of this function. You have to consider this function on the sphere, really, right?
Right. I mean, sort of critical points in the right constraint sense.
So I don't know, maybe, but you know, computing critical points, it's very complicated, right? Because you have the it involves the integral, this integral, right? So you have a condition for the critical points is it's very complicated.
Okay, any other questions? Oh, there's a question on chat. At a high level, do you have thoughts on why all equal maximizes entropy?
Yes, because so first of all, it maximizes the entropy in that particular case. So there are other cases where other random variables xi such that this is not the case. But you know, the intuition supporting the equal coefficient conjecture or the cases when this is true is probably central limit theorem. So there's this entropic central limit theorem, which says that if you take the sequence that appears in the central limit theorem, which is, you know, x1 plus xn divided by square root n, then the entropy of this increases. So this somehow tells you that, you know, well, it tells you that if you have, so let's say, coefficients of the form, you know, equal coefficients 1 over square root n, and then you also have the coefficients n minus 1 coefficients, 1 over square root n minus 1, and the last one is 0, then you have comparison. So it shows you that somehow, at least in this case, making the coefficients equal increases the entropy. But so I showed on the second slide probably that that Gaussian has the biggest entropy among all variance-1 random variables. So if you believe that, you know, having all the coefficients equal makes the random variable look like Gaussian, or makes it the most Gaussian among all the random variables that you're considering, then this is the intuition. But you know, there are cases when this intuition is just false. So this is, yeah.
Thanks, Piotr. Any other questions?
Piotr, in the, I'm not sure what to say it, like what to call it, reduction step that you have, that it only takes 2 coefficients to make them equal. Is the inequality strict if they're not equal?
Yes. And this is actually important.
Mm-hmm.
There, so, yes.
So
do you need a continuity? Sorry?
Do you really need a continuity argument then? Since you can prove that, you mean the continuity arguments to prove there is a maximizer?
Yes. So there is some continuity in the argument. Yeah, yes. For the existence of the maximizer. And you know, in the paper there are, you know, the proof has like 10 pages or something like this, and there are some technical issues. but once you get the right idea, you know, you just figure it out. It's not complicated.
Okay, thank you.
Yeah, you're welcome.
Okay, any other questions? Okay, I guess maybe we are ready to wrap up for today. Thank you all for tuning in.